welcome to Algorithms Live, and this week we're going to cover segment trees. They're pretty well-known data structure and competitive programming, fairly useful. They come up a lot. I'd almost say they're a way of thinking about problems that require a data structure more than a specific data structure themselves. And a lot like dynamic programming, you can modify them for different uses. So today I'm going to teach you how they work, but I'm also going to be teaching you in a way that opens it up for modification. So that way you don't just use it for the classic purpose, which is solving this range minimum query problem. You'll be able to extend it to a bunch of different applications. And hopefully that'll be really useful. This data structure does go by a few other names, though. I've seen quite a few. So one of them that's quite common is interval tree. Of course, there's another data structure in academia called interval tree that also gets talked about a lot, and it's not the same as this interval tree. Same thing with segment tree. If you go on Wikipedia, you read about segment trees, they're not talking about this data structure. Another name I hear is tournament tree. And this is what the Croatian Olympiad calls it. So I read their solution guides every once in a while, and they'll refer to this as a tournament tree instead of segment tree. And that's also, there's another structure called tournament tree that you hear about. So that can be a bit confusing with this name tournament tree versus interval tree. And I haven't really seen a better name that avoids the conflict with academia. It's like they called dibs on these names first. And this data structure came about that is a data structure on segments, and we're stuck calling it segment tree. And now we have this weird, awkward conflict. So just something to deal with here. But whatever the case, this data structure in particular is super useful. We also have this, a little bit of housekeeping before we begin too. If you have a specific algorithm or data structure you'd like to see on the show or like to hear, just leave that in the comments below on this video and I'll try to get to them. I have a few things planned. I do have a guest being planned right now for future weeks, and a pretty exciting guest. And I won't reveal the name until we schedule him, but it should be exciting. I know you all enjoyed Dion, so something to look forward to. And if you have suggestions for guests, leave them in the comments below. I'm going to be trying to invite more and more guests on as we progress on the show. But back to segment trees. So here's the first idea. I wrote in the blog about wanting you guys to review how merge sort works. Because really what a segment tree is taking the recursion pattern of merge sort and turning it into a data structure. So there's this thing called divide and conquer on trees, and some of you may have heard of centroid decomposition trees. Well, it's taking the recursive pattern of divide and conquer on trees and turning it into a data structure. Here, we're taking the recursive pattern of merge sort and turning it into a data structure. And so anytime you have a divide and conquer style recursion, you can pretty much turn it into a data structure. And that's why I'm bringing this up. So roughly speaking, this is what it looks like. So you have a list, you cut it in half, and you end up with two lists to recurse on. You go down the left branch, you break that into two lists, and you keep going down until you're left with just one list on the bottom level. So maybe we'll skip that level, and we'll just say this is the bottom level. And we recurse back up the tree, and then maybe we go down this side. So we take our left child, recurse down the bottom level. And on each level in merge sort, because you loop over the array to split it in half, that's a linear amount of work. And on the way back up, you combine two sorted lists in linear times. It's a linear amount of work. So this rectangle basically denotes that linear amount of work. So you can use this to analyze merge sort's runtime. This is probably the best visual example of why merge sort is n log n, because this width right here is the width of the array, and that's O of n. And this height right here is going to be log n deep. Notice I'm splitting the array in half. If I just look down the left side of this data structure, I'm splitting the array in half in each time. That's binary search, and we all know that's log n. So this is a log n side on the left. And now if you just look at the area of this box, the area of this box is n log n. So I can actually analyze merge sort with pictures, or at least visualize the runtime. So this helps me think about how merge sort works. All right, so how do we turn this into a data structure? Well, I could say that this is the root node. It's the entire interval. Everything is covered. And then I look at the different sides, and these are all nodes. And that's how I'm going to form my tree. So I'm taking the recursion tree of divide and conquer on sequences, which is how merge sort works. And I'm just going to turn this into a data structure, and particularly a binary search tree, or a binary tree. Instead of each node, so on the bottommost level, that's storing my array, basically. And on the intermediate levels, I'm storing information about aggregate sums for the different subtrees. So I get ownership over different subtrees. So I'll give you a quick look at what this looks like. So the root node, let's say I have a sequence from 0 to 7. The root node stores the whole thing. So it stores a sequence from 0 to 7. Let's center this a little more. Okay. Whoa. Break that up. So then my left child, I'm going to split it in half, just like I would binary search. Or binary search, or, yeah. Split my data in half. Merge sort. So then I split again. 0, 1. And 1, 2. Over here, 3, 4. Ooh, messed up. 4, 5. 6, 7. And then the bottommost level is actually storing an array. So they're size 1 ranges. 0, 0 inclusive, 1, 1 inclusive. Ooh, I messed up here too. There we go. 2, 2. I think I was using a smaller marker size. So let's 3, 3. And that's how this thing is organized. So now, if you watched the trees episode, episode 1, we talked about subtree aggregates. We could store information about our subtree in the intermediate nodes, and it would give us more information about what's going on in that level. So what I'm going to do first is I'm going to implement a way of maintaining the range minimums over the entire range. So I can store information. So if I knew that 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, those individual nodes had particular values. So in this case, it could be an array. Well, I could store subtree information in my parent nodes. So the min of 2 and 3 is 2. The min of 2 and 3 is 1. Just taking this one. The min of 2 and 8 is 2. The min of 7 and 4 is 4. And I can keep pushing this up the tree. So I could have this nice static tree that stores information about its subtree. And at every level of the subtree, I know for a particular range what's being covered. Okay, that's all fine and good, but let's say I want to know some information about range minimum queries. So that's what you see with ARM-Q. How can I use this structure to get information about what's the smallest number stored in some range? So the query looks something like this. Given some range ij, report min. All right, so let's take a look at some example queries and see how we go about doing this. So let's say I do a query from 2 to 7. So what I do is I start off in my root node, and I'm looking for intervals that are completely covered. Well, I don't completely cover this root node. I only cover part of it. So I'll do a search down my left and right child. So I'll go down the left child first. 0, 3 is not completely covered by 2, 7. So I'll go down my left child again. Well, this is completely disjoint from 2, 7, so I can stop. Don't have to cover it at all. So that doesn't get touched. Then I go down my right subchild. 2, 3 is completely covered by 2, 7. So I can return up the tree this value of 1. That's going to be my range min. I recurse back up the tree, and normally in a binary search tree, you only go down one path in the binary search tree when you're looking for something. Here, I'm going to go down another path. So I'll actually go down this right path, and I'll be looking for 2, 7. Well, it completely covers 4, 7. So I'll return the min there. So I'm going to return this 1. I'm going to return this 2. They come up to the tree. My min on the range 2, 7 is 1. And that will be my answer. If I look at my tree at the very bottom, 2, 7's range minimum is 1. This is the smallest value that exists in the range. And that's exactly what I wanted to find. Let's do another query, get a better look at this. So I'll change my query from being 2, 7 to being 1 to 4 inclusive. All right. So I'll go down my left tree. Well, I'll change it to blue so I can distinguish it. I'll go down my left tree. And then I'll go down my left tree again. I'm still partially covered by 0, 0, 1. And then I go down my right tree. And I found at the very bottom, actually, I'll even go down my left tree here. And then that's completely disjoint from 1, 4. So I'll return. So this is something I didn't have to consider. I'll go down my right tree. I'll see I'm completely covered. So I'll just return 3 as part of my solution. Come back up. Then I consider 2, 4 or 2, 3 down this right subtree. And I see 2, 3 is completely covered by my interval 1, 4. So I'm going to return right here from this piece. That's completely covered. Then I go down my right subtree. And I have a partial covering here. 1, 4 and 4, 7 overlap. So I'll go down my left subtree. And I'll go down my left subtree again because I have a partial cover. End up finding this element 2, and that's what I end up returning. And so I end up taking the min of 3, 1, and 2. And that'll be my answer for the range 1 to 4, which happens to be 1 again. What you should be noticing in this example is it seems like I'm doing a lot of work to do this range minimum query. I'm touching a lot of nodes. It's not like a binary search tree. So you'll notice this has log n depth, right? The range is being cut in half each time. So I know it is log n depth. But I'm touching more than just the depth number of nodes. I'm touching a lot more nodes. So how do we analyze this runtime? Because it looks like the thing you should be a little bit concerned about is it looks like it should be slower than log n because I'm touching much more nodes. And if you're having that feeling, you're thinking in the right way. But let's try to analyze this. So if I'm doing a query like 1.4, let's put 2 bars here on the root node. And I'm basically following, 1 bar is following the left seam of my query. The other is following the right seam of my query. And they're going to walk down the tree whenever one is getting a partial overlap. So they both start together. It goes down this left seam here, goes down this left seam, and then down to this node containing 1.1. If I follow my right bar, it goes down this piece, and then down this piece. Notice this bar has a unique path from top to bottom, or it may stop early in the case of the 2.7 query. If it's completely covering a range, it can stop early. But there are at most log n nodes it touches if we just analyze each of these bars. Now, we may mark or explore the opposite node from this seam at every stage of the search. But that's just a constant factor more than what the bar is touching. So it's touching at least, or at most, 1 more node than where these bars touch. So if I follow the left side of my query, it's touching log n nodes. If I cover the right side of the query, it's touching log n nodes. And if it's not on the seam, it's just going to return right away. Either it didn't find the answer, or it completely covered the interval and it returned what was there. So I put those 2 pieces together. You'll notice this is going to be a log n query. So it speeds up the query time considerably. So I could form a data structure like this just to use ARM-Q. There's another data structure that does ARM-Q pretty well. So it doesn't seem like segment tree has an advantage yet. But that's where we end up going to this next technique that I think is really powerful, and it's called lazy propagation. So maybe I'll bring my sizes down. So I have this thing called lazy propagation. And what lazy propagation does is it allows you to make changes to your sequence by affecting the tree in a lazy way such that those changes realize themselves as being fast. So what we're going to do is we're going to try to implement this operation with lazy propagation called increase range. So we pass in a range I and j, from I to j inclusive, and we pass some value that we want to change the range by, and it's going to increment pieces of that range up or down, and yeah, and we can modify it. So we could, in terms of looking at this as an array, so I'll let you look at this as an array. I could take some range like this and say increment everything by 2. Well, now this becomes 6, this becomes 4, this becomes 6, this becomes 3, and now my update is done. So conceptually, that's what I want to do. I want to have some sequence, be able to increment the ranges, but then still be able to do my queries like min query or max query or sum query. We're going to be able to do all those queries, but also be able to increment some range. And that's our goal. So I'll write out segment tree again. I'm going to redraw this because we're going to be doing quite a few queries. So I'm going to do my size 7 one. I have to do the leaf nodes. And this is how I'm going to handle the case of lazy propagation. So now I have a new objective here. I'm not just storing the range minimums anymore. I'm also storing a change that I'm going to try pushing down the tree. So what I need to do is keep track of some kind of delta to store subtree information. So in this version of the tree, I'm going to assume that everything is initially 0. And all the sums are initially 0 as well, or all the mins. So everything is 0 in the tree. And now I want to push changes down to my children. So I might say that range, let's do 2 to 3, for example. 1 to 3. We'll do 1 to 3. Perhaps what I want to do is I want to increment all nodes from 1 to 3 by 5. Okay, that sounds reasonable. So I start in a very similar fashion to how I was doing my min queries. I go down the tree left and right. And when I get a complete covering, so right now I'm doing the interval 1 to 4, or 1 to 3. Yeah, it shows 1 to 3. And I'm trying to increment it by 5. When I get a complete covering, in this case 1, 1 has a complete covering, I'm going to increment my delta by 5. And I'm going to keep the subtree sum the same. So I go down the right subtree. I get a complete covering. So I increment my delta by 5. And I keep the subtree sum the same. When I come back off my recursion, so on the back end of this recursion, coming back, I'm going to take the delta and the min value, add them together, and update what my min is. So my min here is 5. Well, my min here is actually the min of the left and right child, so it's actually 0. But here, the min left and right is also 0. So that ends up getting changed. I come back up the tree. But notice I'm not pushing this change all the way down. I'm just keeping these values lazily at the node they're at. Let's do another change. I'll increment 0 to 7 by 1. Well, 0 to 7 completely covers its range, so its delta is +1. Now I can do another update. I'll do 2 to 5, so you can see how these changes work, and I'll add 3. So if I get to a node and it has some delta to push down, I need to push it down to its neighbors. So I'll push +1 down to the left child, +1 down to the right child, and then remark the delta as 0, or get rid of it entirely conceptually. So this is what I mean by lazy propagation. I'm basically saying this subtree needs to augment by +1. But then when I finally get to that node and I need to process it, that's when I push the change down. Changes get aggregated. If I move down the left subchild here, I get to this +1 again. It needs to push its +1 change down to its left child, and then push its +1 change down to its right child. So I get +6. So I get down to this node. It's +6 coming back up. I need to update the min. The min is between 1 and 6, so I store it as 1. Go down my right subtree. I have +1 here. Oh, I also have to do +3, so this should actually be a 9. Oh, well. So then I go down my right subchild, go down my left subchild, and I also have to implement this +3. But I also pushed down my +1 change as I went. And so I increment the min. And so my min over my entire tree is 1. But now I've got all these lazy augmenting deltas that are up and down my tree at a given time. So I can also do min queries like this. So let's say I want to know the min value for 1, 1. You can intersperse updates and min queries all together. So I'll go down my left subchild. I get down to 1, 1. This change gets propagated, so +1, +6. Now I can update my min value. I know that the answer here is going to be 6 for 1, 1, because the change got lazily propagated down. And on my way back up the tree, I save what the true min value is, because at all times I need to know for a given subtree, what's the min value in that subtree. And so that's the idea of lazy propagation. I have some values that I want to push down the tree, and some values that I want to aggregate from my subtree and know what's coming on. Another thing about updates is they have to aggregate well. In the case of addition, I can put two additions together to form a larger addition, which is the whole reason why lazy propagation is actually fast. One change is only one change. If you're mixing increments with some other operation that doesn't mix well and doesn't aggregate well, then you're not going to get this speed up that lazy propagation provides. So things to think about when attacking these kind of problems. So let's talk about implementation details, because I'm actually going to implement one of these for you, and then it'll give you a better idea of how they work and how you structure your code so that it's easily modifiable. So if you're using C or using Java, one way you could code this is you could save left and right pointers. You can make a node class storing information about the maxes and mins. You could have a left pointer. You could have a right pointer. You could do the balanced binary search tree and like figure out how that works. But the way this thing is organized, we can guarantee its log-in depth. And we can also guarantee that it's never going to rebalance or rotate. So if you're thinking of AVL trees, treeps, any kind of binary search tree that rebalances itself, segment tree doesn't do that. So this is kind of wasteful having these left and right pointers. And in practice, it's a lot faster to implement this as an array. And so here's how we're going to structure this array. If we're at node I, the left child is going to be node 2i, and the right child is going to be 2i plus 1. And we're going to make the root node of our tree 1. So I'm going to store the entire segment tree as an array. The root node is 1. The left child is 2. Right child is 3. Left child is 4. Right child is 5. Left child is 6. Right child is 7. And you'll notice through the levels of the tree from right to left, that's how I'm labeling this tree. Left to right. So 8, 9, 10, 11, and so on. It's a very nice numbering scheme. If you try to do this starting from 0, it doesn't work too well. 2 times 0 is 0. So you're going to waste index 0 of your array if you're in Java or C++, because everything is 0 indexed. But that's OK. That's just one cell of memory. We're not going to lose sleep over that. So that's basically how I'm going to implement this data structure. And without further ado, let's actually implement this thing. I've got some test code in here that you'll see in a minute. And I'll implement one from scratch and just talk about what I'm doing at every step of the way and how I'm making it easier on myself to actually implement this thing and make it usable. Get set up. All right, so I have some test code in here you can ignore. Yikes. There we go. That's what I wanted to see. So what I've implemented here is a thing called query interface. I'm using Java again. I know some of you don't like that, but you can adapt this to C fairly easily, or C++. So I have two operations, increment range. So take everything as range, increment everything in my data structure by value, and get me the minimum over this range. So I've implemented a really naive version of this that's just a for loop from I to j that's incrementing all these values k in my array. And for the minimum query, I just do a for loop over this range I to j, increment all those values in that range. So this is my slow version. I basically just implemented this so I could test my segment tree when I'm done coding it. So I recommend you do the same when you're coding a segment tree. This way you can catch your bugs and make sure it works before trying it on a problem. Okay, so I'm going to implement this segment tree for range minimum query. So the very first thing I need to do is I need to initialize my segment tree. I'm going to store a few pieces of information in each node of the segment tree. So I'm going to have a big, long array. The ith index tells me information about the ith node based on that numbering scheme that I talked about. So I had this 1, 2, 3 numbering scheme. These are the indices in my array for my segment tree. And what I'm going to pre-compute first is these range intervals for each of these nodes. So I'm going to write an init function that's basically going to tell me for every single node ID, what is the range it's responsible for in the node. Okay. So I'm going to have low and high. So this is low is the low end of the range, high is the high end of the range. And that's what I'm going to initialize. So how big do I make this array? 4 times n plus 1. So if you have a binary search tree with n leaves, it's going to have n minus 1 internal nodes. The reason for that is if you took all the leaves and you were merging them with intermediate nodes, you end up with n minus 1 merges to merge all those intermediate nodes. So our tree is going to have at least n plus n minus 1 nodes. But if we go one layer below that, because it's not going to necessarily be balanced. So if I look at my version here, I drew it a completely full binary search tree, but it could have a partial level field. Some of these nodes might not be present. In that case, that's why I need a little bit extra buffer room. So I need 2n extra nodes to be the level below all my leaf nodes. So that's where I get that 4n from. I have 4n, I get high, 4n plus 1. I get high and low. Let's start writing init. So I'm going to pass in, I guess, 2 pieces of information here. I'm going to pass in the range I'm trying to initialize and the node that I'm currently on. So when I call init, call it on the root node, and from 0 to n minus 1. I'm thinking of this as an array of size n. My indices are 0 to n minus 1, my data structure. Okay, let's look at init. So low of I is going to be A, high of I is going to be B. And if I ever come across the case where they're both equal, I know I'm at a leaf. So in this case, I can just return. Don't need all that. Now I need to look at my left and right child. So I need a split point for my array. Should look just like binary search. I'm taking the midpoint between A and B. So I just do A plus B divided by 2. And then I call init on 2i, which is representing my left subchild from A to M. And then I call init on 2i plus 1, which is going to be my right subchild, and do m plus 1 to B. And that gives me a init for my range. Okay, so that's all I have to do to initialize my segment tree. Let's talk about some other values we're going to store in here. So I need to keep track of range minimum. So I'll call that min. It's going to tell me the min over my entire subtree range. I'm also going to keep track of delta, which is the change I have to push down to my children once I get updated. So those are two new arrays that I have to add to my structure here. And they're just two pieces of information I'm adding to my segment tree. I have a min and I have a delta. So I want to implement increment and minimum. So I'm going to make versions of this that also take in a node value. So the very first value is going to be which index in this table am I? In other words, what's my node ID for my current segment tree piece? So I'll have a special function for increment and also a special function for minimum that takes in node IDs. Let's start with increment, try implementing that. So one thing that's going to happen when I'm going to be coding increment and minimum is there'll be changes that I have to push down to my children whenever I touch a node. And there are going to be changes that I need to aggregate up for my children whenever I'm done touching a node. Because I have to store the aggregate minimum, but I also have to store the change that I need to push down to my children. So I'm going to write two helper functions called prop and update. So prop is propagation. So it's the lazy propagation piece of the segment tree. That's me pushing my delta change down to my children. So in this case, what I'll do is I'll update my left child by delta, my current node. I'll also update my right child by delta. And then I'll reset my delta to 0 because I've already pushed my change down to my children. And so update is the aggregate update function. I'm going to update what my range minimum is. So min of I is going to be the min value of my left child plus its delta value because it might not have pushed its change down fully. And then the min value of my right child plus its right delta because I haven't pushed my change down fully. Now with these two functions, the reason I code them as helper functions is if you have these two functions, this is what really changes between segment trees. So if you have a different kind of update, like let's say take the XOR of all the values with this current value, you can change delta instead of being plus to being an XOR operation. If you want it to be max, you just change this position to be max instead of min. Or if you want it to be range sum, you could adjust it so that it can handle range sums. So coding a prop and update function gives you a nice template for your segment tree that makes it easily modifiable to other purposes. And so this is why I code it this way, just so that way I have minimum amount of code that I need to modify in order to get my segment tree working. And most segment tree problems aren't range minimum queries, so this is a really desirable trait for the segment tree that you're coding. Let's go back to increment. Remember, we have a few cases here. This is the interval that we want to increment all the values by. So if this interval from A to B doesn't cover this range that we currently are, then we need to kick out of the recursion here. So here's what I do. I look at the upper bound, and I see if it's less than low. So this is basically handling this case. This is my query interval. And I've noticed that the interval that my segment tree is holding, it's to the left of that. This is low of I over here. And this is B right here. So I'm handling that case with the left side of this. The other case is if my query interval, if it's not covering it, it's going to be the right side over here. So I need to compare the high value of my node. And if that's less than A, these are both the two cases where I need to kick out. There's nothing to do here. This is outside the range I was trying to update. That's the first change I can make. Let's look at the second change. What if my interval is completely inside its node's coverage? Oh, got that the wrong way. Hold on. Yeah, what if this interval that I'm trying to cover completely covers this node? In this case, I know the change is being applied to this node completely. I can increment my delta at this position by my value and then return. I've completely covered this subtree. Now this down here is the partial cover case. I've handled the case where I've completely covered or not covering, so all I'm left is with some kind of partial cover. If I've gotten down to a node with a partial cover, I need to push my change down to my children. I might have some lazy change that's currently in this node that needs to move down to my children. So at the start of any recursion, you should get in the habit of calling propagate first, so I can push this change down to its children. And then now we can do the two branches of the recursion. So this is me going down my left branch. And I can do the same going down my right branch. And that increments the range. Now I'm coming back from my recursion. I need to store the aggregate minimum for this entire subtree. So I've walked down this subtree. I've updated all its values. Coming back off the recursion, I need to know for this subtree what the min of that entire range is. So I can just call update here. So sometimes you'll be coding a segment tree problem, and you don't need to do a range query for the minimum. You just need to implement this increment, but then also be able to do a query of the range of the entire tree. Well, that's going to be stored in min of 1, because min of 1 is holding the entire tree worth of min values. So if all you need is the min over the entire sequence or the entire array, you don't even have to code the range minimum query piece. You can just code this first increment piece and be done and not have more code to debug. But sometimes you need the range minimum query piece, and that's what I'll code next. Okay, and before I move on to that, I'll look at some of the questions. Does the min value need to be initialized to infinity? No, the only thing I'm doing here is setting my min value to be initially 0. So I'm assuming the entire range is 0. And when I want to start adding values to it, I'll just call increment on the index twice. So I'll call increment on 0, 0 if I want to increment the first node, or 1, 1 if I want to increment the second node. I just increment those values and fill the array that way. Alternatively, I could pass in an array, and then just in init, when I hit this particular node, I can mark that as the min value of my initial array. And as I'm coming back from the tree, I would put a call to update right here. And that would allow me to implement this so that it's doing range minimum query. This is great if you need to do armq without the lazy prop or increment. You could just initialize the entire array, then do armq without even having lazy prop in the data structure. So that works perfectly fine. Yeah, and I think that does it for questions at the moment. So we'll move on to the minimum query piece. This code is going to look a lot like the rest of armq. So once again, I'm going to look at the outside the range case. So A and B is outside of the range I'm trying to cover for this node. In this case, what I'm going to do is I'm going to return a large value because I'm going to be minning this with other values in my segment tree. So I return a sufficiently large value. So when I take the min, what is actually in the range overtakes this large value. So since my segment tree is on ints, I'm just going to return integer.max value. I could use longs, return long.max value instead. Okay, so then I also have the complete cover case, which is low to high. So now I have a complete cover over a segment tree. When that occurs, I just return the min of what's currently there plus the delta of what's currently there. There might be something in my delta. That's OK. I'll handle it in that case. So now I have the partial cover case again. So I'm going to have to prop and update before and after I do my recursion. So I'm doing a query. I want to know what's the covering on the left subtree and what's the covering on the right subtree. So I'll recursively call minimum on my left subtree from A to B, and then call min right to do my right subtree. Put those two pieces together. I just return the two subtrees. And voila. That's how you implement minimum. So I push my change down to my children. Then I try querying the left subtree, the right subtree. Now, I don't update my min using this min and left and min right, because this might be a partial cover on my left tree or my right tree. So it's good that I keep those two updates separate. So it's another advantage of writing a separate update function. And then I just take the min of what the actual query values were, which were these return min left, min right. And then I take that min and push that change down. So good practice would be trying to figure out, there's versions of this, try to change this update, instead of being min, being sum. So that's a really fun one. You really shouldn't have to change a whole lot to do subtree sums. You basically store that, and you just change this update function to be sums and deal with it that way. You also, another fun one to do is calculate the min value of the subtree and the number of values, or the number of things in the tree that have that min value. So you're returning two values now. That's another good practice piece when you're starting out with segment trees, playing around with that version, seeing how it works, and you can implement a segment tree in that way. But for starters, a problem I recommend doing if you want to code a segment tree from scratch and then test it against mine, there's this problem called circular RMQ. It's on Codeforces, so I'll write the name in here. There's a problem called circular RMQ. You can test out your segment tree, run it that way, see if it's actually working. But speaking of code actually working, let's see if my code is actually working. So what I've done here is I have a small test infrastructure. So I have my range slow code and the segment tree code I wrote. And I'll see if it works on my small test. So I have some updates here. So 1 means increment all the values from like 0 to 3 range by 2. And 2 means do range minimum query on 0 to 7. So we'll do a quick test on that. Let's see if this thing compiles. Well, it appears to be working on the small test, so let's try a bigger test. So I have a size 100, and it's randomly making these events. So queries and updates, just completely making some random ones. This one's not going to print out all the tests. All tests passed. So I tested it against my range slow version. And then just to prove that it's fast to you, I'm going to do 1,000,000 queries. So I better take out range slow. I'll just put in a second segment tree. So I'll do this operation, test the segment tree against itself. Of course, it's always going to have the same behavior, but at least it'll test if it crashes well. And you'll get a feel for how fast this thing is. And it passed all tests. So that was 1,000,000 queries. Usually a segment tree problem, you see like 10 to the 5th updates or size of the array. But there's also, this computer I'm working on is also pretty slow. So don't freak out that it's not running super fast. So that's pretty much all we have this week for Algorithms Live. I encourage you to tune in next week. Be sure to leave some comments on the video, things you'd like to see in the future. If you really want some topic covered, or if you think of a great problem that you want to see covered, talked about, I'll be happy to put that in to cover for you guys. Have some good topics in the future weeks. I'm really trying to vary the content here too. So I want some more advanced content some weeks and some a little bit more basic content that people starting out, they can get the hang of these data structures and these algorithms. And each week I'll try to make something that, even though it's a simpler concept, something may surprise you. Try to relate it to various things that I happen to know from competitive programming. So hope you guys are all enjoying the show so far, and leave comments in the blog, or leave comments on the blog, or leave comments on this video. And yeah, I'll try to cover some really cool stuff. And I hope to have many more guests in the future. We're getting that second guest lined up, and hopefully he'll be on next week, but we'll see. So tune in next week. Can't wait to see you. And that's all.